What's up, guys? And today we're in another video. I figured I'd release a physics video, and the physics concept that I chose for today is simple harmonic motion. This is a simple video. This is how I studied simple harmonic motion, and if you're currently taking a physics course, then this video may be for you. I sure hope this is helpful. So simple harmonic motion, the first thing that I think about is that according to the research that I made, simple harmonic motion basically refers to an oscillatory motion in which the force exerted is directly proportional to the displacement. Yeah, and simple harmonic motion specifically also ties into the connection of Hooke's law, where Hooke's law can be stated as the force exerted on an elastic string, which is directly proportional to the extension caused by the compression on the string. And so I'm gonna go into detail. So the equation that you see here is Hooke's law. It's an example of Hooke's law. F is equal to negative kx. F stands for elastic force. It's the force exerted on a spring. And this is an example of a spring. We're gonna get to that. We're going to get to also why this is a simple harmonic motion. The negative just refers to the restoring force. It just means that it comes back. Once you exert it, it returns. The K that I'm pointing on is the spring constant, and the X is the displacement that the body moves from the mean position, and we're going to get into that from the diagram below. A simple harmonic motion can also be described as the acceleration that is directly proportional to the extension that is directly proportional to the displacement of a body being compressed from its mean position to when it's extended. So I think this ties really well with the common equation of in physics F is equal to ma, where where F is the force, m is the mass, and acceleration is represented by a. So the same way you can describe simple harmonic motion to be either the force directly proportional to the displacement or the acceleration directly proportional to the displacement, that's the same way it ties into the fact that the force exerted on any body is directly proportional to the acceleration that is produced by that body once a force has been applied. And so now let's go into the specifics as to what this diagram means. This is an example of a simple harmonic motion. Remind you that simple harmonic motion is the oscillatory motion performed on a body such that the force exerted is directly proportional to the displacement of the body from the mean position. So this is an example of a pendulum. You can think of this as a pendulum, as a ball, or any other object, or even as a particle, depending on the field of study. So like in chemistry, we would think of this as a particle in case you want to understand like the vibration behaviors of a particle in space. That's mostly why simple harmonic motion is really important in chemistry. But in this video, we're going to explain why it's important in physics and why it is important in other fields, respectively, like chemistry. So we have the example of a ball here. When you can, and it's suspended by a string tied to the wall. And so when you stretch this ball forward, you're gonna be extending the ball. So it's gonna displace from its natural state of position, which we refer to as the mean position, and then it's gonna get displaced further down. So you're gonna essentially, that means you're gonna elongate the string, and then once you elongate the string, it just ends up oscillating immediately, right? It starts oscillating up, down, up, down, up, down. That's what goes on. So when it's why I represented this as negative a is maybe, for example, like a decrease in the it's negative A, maybe for example, when it becomes shorter, and then it's positive A when it becomes longer. So elongation, constriction, elongation, constriction. And so there's this simple harmonic motion that comes into play. But when the ball is in the negative A position, allow me to say, when it's in the negative A position, it exerts the most amount of potential energy, which is described in this graph. So this is where the ball is at negative A. So when you extend this ball all the way here to where it cannot go any further, that point we normally recognize it as one of the extremes, because the ball would not be able to go any further. The only way it can move from that position is when it returns, when it exerts a restoring force to combat the action being exhibited on it, if that makes sense. So what I'm saying is, when you exert it to one of the ends, it immediately restores itself to the other extreme. Does that make sense? So what I'm saying is, from negative A, it moves through the mean position, which is labeled here as 0, to the other extreme, which is labeled as A. So what I'm trying to get here is, at negative A, it possesses the maximum potential energy, because at that point, it's not going to be moving. But immediately it starts moving, the potential energy decreases till it gets to 0. At the point at its 0, its kinetic energy is at its highest, meaning that it's full on in motion. It's not going to stop during that oscillation period. And so from 0, it continues till it reaches the other extreme. And when it gets to the other extreme, it possesses the most amount of potential energy until another oscillation is performed. And so it oscillates. That's what ties into simple harmonic motion. It oscillates continuously from one point to the other. That's what we mean by oscillation. That means that it moves from between 2 points, in and out, up and down continuously, because a force has been exerted on the body, and this particular body has been tied to the string. That's why there's this oscillatory property associated with this. And to make things easier, I'm going to label this as PE curve, as opposed to the PE curve. You can also draw a kinetic curve, kinetic energy curve, right? Kinetic energy curve. So what does this mean? This means that when potential energy is at its maximum, kinetic energy is the lowest. As the ball moves from its extreme to the middle position or the mean position, it's full on in motion. So potential energy is at its minimum, because the ball is not going to be stopping at that point, but it's going to be highest at the kinetic energy. So now once you pass the mean position and head to the other extreme, the ball is going to stop momentarily and then continue on in motion to perform a second oscillation. So when it stops momentarily, the potential energy gathers till it's the greatest, and that's represented at this point of the curve. Whilst the kinetic curve, it's at its minimum, because since it's momentarily stopping, it's not going to be moving any further than that, unless it exerts a restoring force so that it reaches to the other extreme. I sure hope this was helpful. I hope it gives you an insight as to what simple harmonic motion means in the field of physics, in the field of quantum mechanics, whatever you're going to be using it for. I sure hope this was helpful. Please like and subscribe. Comment in the comment section where you want me to expand upon more. If you have any questions in other related fields, I'm more than happy to explain. And as always, I'll see you in the next one. Please like and subscribe. Bye.